My name is Mikołaj Wielocha, and I work for YouGov. As you can see, all the slides are branded. Sorry for that. But yeah, and I will be talking about how to create a real-time, modern, scalable web applications. It's kind of it's not very, I don't know, detailed description, but we'll get to that. I will explain exactly what I mean, and we will come to some more, I don't know, more familiar terms and definitely more trending terms later on. So yeah, first of all, well, basically the whole presentation wasn't meant for a live coding session at the end. So there will be some code on the slides, but we will try to re-implement that later. Well, actually, parts of it, because there's no point in doing everything. But basically, okay, so the whole idea for the concept I will be talking about here actually was given to me by my colleague from YouGov. He was doing a very similar presentation on the Warsaw Python Summit this year, and he was doing this in Python using Postgres as a database, and he was also like focusing on the real-time part of it. Because we code in Scala, as I assume everyone here, we will try to focus more on the other parts, but real-time as well. Basically, yeah, so real-time. What is real-time? I think we all have intuition what that means. Basically, we need to keep the user of our web application informed about what the system is doing at the moment all the time. In real-time, that means just after he performs an action. And yeah, and we have the tools right now on the front end because of, for example, Websockets, or maybe that's all there is actually, but anyway. And so we should try to adjust our backend for that. I am assuming that most of you are backend developers. So yeah. And this is one of the biggest principles of the front end, of the usability feeling of the application. It has to be as real-time as possible, although like previously it wasn't really possible to do on the internet, online. Yeah, so the other part of the problem I will be talking about is scalability. And so maybe some of you already know where this is going. But anyway, scalable means elastic, in other words. But when we create web applications, we need to think about scalability of the whole system, as well as every single part of it. So for example, my colleague, he was using Python. This is probably, he was using his own framework, if I recall correctly, for web application. And it was probably stateless, I don't remember, probably it was. But he was still using Postgres underneath. So it wasn't really scaling, because he could spawn as many web applications he would like, but still there was only one Postgres. I know you can do some scaling with Postgres, but this is not really scaling. This is the main principle of relationship databases is that you have some sort of association between tables, and that really spoils the whole concept of scaling. But so I will tell you about an alternative. And so the last word, modern, is about being resilient and message-driven. So we have real-time, which is basically responsive. We have scalable, which is elastic. And modern is what's left, that's resilient and message-driven. We'll not talk about resiliency because that's not the point of this presentation. But all that together is reactive, according to the manifest. So yeah, basically we will be talking about how to actually make a reactive web application here using Scala, obviously, but also some other technologies. And each one of those technologies actually is about everything that the reactive manifest is about. So we have Cassandra, we have Akka, which is kind of, I added here like an Akka stream example to consume rabbit messages. This is kind of why? Because it's fun, basically. There is no point really in that in terms of the whole concept of the presentation, but it is nice to have some additional funky stuff. So we will be talking about Cassandra, Play, Scala, obviously. We will not be talking about HTML because I don't really know nothing about that. So a part of that is about Websockets. And message-driven, for that we'll be using RabbitMQ. As we all know, it's also very scalable. So let's start with Cassandra. How many of you ever use Cassandra in a commercial product? Well, that's good, although I thought it's more popular right now. But anyway, so basically Cassandra is about scaling. You can have as many nodes of the database as you want, and they scale almost perfectly. So the fun fact, the biggest production deployment probably is Apple's. Although, for example, Netflix also uses Cassandra. So I don't know if they share how many nodes they have. But basically, Apple Maps utilize Cassandra, and there's a Spark cluster above that. And so whenever you, for example, call Uber from your iPhone, you are probably executing a query against Cassandra, a Spark query against Cassandra. But probably it's cached somewhere, so maybe that's not even true. But anyway, and starting with Cassandra 2.1, actually right now there is a 3.0 version, but it's not really production ready yet. They introduced a mechanism for creating your own triggers. That wasn't there before. So you can actually react to any change that occurs on the table, although it's not really a table. Right now you can basically use Cassandra using a query language that's called CQL, probably Cassandra query language, just like that. And you have tables in there. It's really similar to SQL, actually a very small subset of it. But but before that, before they actually introduced the native SQL protocol, there was Thrift. And you had to have a very good knowledge of the Cassandra internals to actually execute any query against that. So it was like not that long ago. Actually, when I started using Cassandra, that was the only option. But that was really nice because I used that knowledge to create my first trigger. This is Java because Cassandra is written in Java, so you implement your triggers in Java. I will not go through this code. It's really messy, and there is basically no documentation about how to create Cassandra triggers at the moment. Maybe it will be at some point. They will probably create one. But right now, this is an experimental feature, so please don't use that in production. But yeah, it's messy and it's ugly, but it works. Basically what it does, this code, any change on a given table, also called column family, well actually underneath those tables that you see in SQL, there is something called a column family. It's not a table because each row can have its own set of columns. And SQL somehow translate that to a more familiar thing. That was their motivation basically to make a language that is more easier to adapt for people coming from a relational world. And yeah, so you have to do stuff like that, but it's ugly and we'll not get into detail. What it does is actually watches for changes on the table and then pushes them to Rabbit. That's it. The point of that is that we want to know when something is changed in our database, basically, so we can, at the same time, inform our user that an event has happened and show him what actually has changed. You probably all know Rabbit, right? Because this is the default, basically, right now. The default in the way that most of the messaging brokers actually if you have a system that utilizes something like that, then it's probably Rabbit. And yeah, so the part of this trigger just creates a connection to Rabbit. You can use any Java library, although you have to remember that when Cassandra launches, it will have to load all your classes and all your dependency classes, and so you have to be careful. But this is only simple Java code with one addition, and that's the Rabbit client. This is all Java we're going to see today. Sorry, that wasn't true. This is all Java we're going to see today. So let's move to Scala. We all know what is Scala. Basically, this presentation wasn't meant for people that actually are familiar with Scala, so let's keep that. And so, yeah, we have an application that is basically a to-do list. That's the best example you can think of. It actually is very nice because it covers most of the cases you actually have with a real-time application. So we're going to be working with a model that looks like this. Those are from Play. Some of you are probably familiar with those. It's basically a type class that defines a, well, actually this one is a macro that generates a formatter that creates JSON from that. I really like this technology, and I hate all the other ones. And yeah, so our application will be fueled by Play. This is basically, in my opinion, the best way to write web applications in Scala. Obviously, Play, well, for those who know how Play looked like in a version 1.0, so this was a kind of a project created by this French guy, Guillaume Bord. He actually created a Java framework. And after that, when Scala became more popular, that was like 5 years ago or something, he added a plugin that you could use Scala with. But that's not the point. But anyway, this is the initial version of the framework was really heavily inspired by Ruby on Rails, although you have types, so that's cool. And yeah, and after that they switched to the second version, which is completely different and absolutely something completely new. But some principles remain. The most important one is that it's stateless, so you can scale it as much as you want, basically. So we have Play, we have Cassandra, so we have to somehow connect one to the other. And for that, we are using Phantom. This is a very niche kind of a library, although it's becoming a default when you use Cassandra with Scala. It's not ORM, obviously, but it has some pretty nice features. This huge boilerplate here is a mapping to your table or column family or whatever. Well, actually, this is CQL, so let's say it's a table. And on that, you can execute your queries. Underneath, the heavy lifting is done by DataStax's Java driver, so you are at home. Basically, it will be developed in parallel to the Java driver, which is nice. It's obviously asynchronous. There is the new I/O behind that. And yeah, it's all that we want. So it's basically reactive, I guess.
So it's like Slick for Cassandra, right?
No, nothing like Slick for Cassandra. And that's a very good thing, because Slick is awful. No, this is much simpler. This is basically very lightweight, very simple to use, and very well designed, in my opinion, although it's not perfect. Basically because of that boilerplate. But this is something you write only once, right? And you can actually write abstractions that cover most of your use cases and narrow down those abstractions so that when it comes to implementing a repository, you don't really have to write all that down because you already have most of it written. And we actually did something like that. And this works basically, this is an example of a usage. So it's really clean and nice. And obviously it has a feature which is super nice and it's really asynchronous. So after that, we come back to Play, implement our controllers, actions. I will not, again, get into detail because we will be implementing those as well. And there is Akka. Akka is the implementation of actor model in Scala. It's very nice to work with, although it's not type safe, but they are working on it. Actually, there is already an experimental version of the so-called behaviors, or maybe it's not, but I don't think, it's still experimental, I'm pretty sure.
Akka type.
I'm not sure, because there was another attempt of creating by Ronald.
There is a new Akka type, and it's still experimental, and it's not at all integrated with other products like HTTP.
That's probably true. Well, actually, I saw a presentation about that on Scala Days last year, but yeah, it was really nice, but there was this comment that is not integrating with anything at the moment. But the whole concept is very nice because you don't really have actors in your actor model. That's really mind-blowing in a way. It's kind of thinking outside of the box. They actually created something that is called behaviors, but this presentation is not about that. You probably can Google it up. So actors and play, well, basically play is based on Akka. The whole HTTP stuff is done in Akka. And for example, the easiest way, or maybe even the only way, I don't really know, to implement the WebSocket is by using an actor. I'm not going to get into detail again about what's going on here. We will see that on the live coding session. So yeah, that's about Akka, basically. We have some stuff that I will be talking more about when we get to the implementing part. And this is the streams part. So our sync, for those familiar with streams, for those that are not, I will get into more detail while implementing. But our sync will be based on an actor, and this is the actor. But let's not pause on this. And yeah, for the connection between Akka streams and Rabbit, we'll be using a library called OP Rabbit. I think it's the best out there right now, although it's again not perfect as most of our libraries. But ours not in terms that we created that, obviously. But oh yeah, actually there is an error here. So basically this is the way you define an Akka stream source that will consume a message from the Rabbit. This won't scale because you actually, well, if you provide the name of the queue, it won't scale. But it will, even then it will not scale because the exclusive is false. And we want to have a cluster of Play framework applications, so there cannot be only one queue in the Rabbit. Even though the exchange is fan out, we need to create an exclusive queue for each of our instances. But that's already fixed in the code, so sorry for that. Anyway, so you define a flow, an Akka stream flow. Again, it's kind of I will show you a different approach here. Basically, what the OP Rabbit gives you is something that is called a acknowledgeable stream. So it's kind of a wrapper over Akka streams. So at some point of your stream, you can say that I acknowledge this message, and it's the acknowledge in terms of the message broker. So only when you say that, you can, well, actually, when you call this method, the message will be acknowledged, and you are back in the Akka stream world, and you can do no more flow here. Otherwise, you would have to, if you want to, for example, acknowledge after the serialization of the message, you have to have an asked flow here. I will show that later. Yeah, and HTML5 for the WebSocket. So, any questions so far? Hopefully not. Let's see how the live. Right, so first of all, I'm gonna mirror my display. And yeah, and we have a wrong version of that. So what we will do, and it's not even working, probably I need to restart everything because my laptop went to sleep, and I obviously forgot about that. But, so yeah, can you see? Yeah, you can see. Cool. It's small, but I don't really want to mess with the console here, okay? So, if you really want to, I can try, but, oh yeah, it's easy, okay. Never done that, to be honest. So yeah, let's see now. Let's remove our local changes. Yeah, it's done. So we have a template. Basically, in other branch, I have the running, well, actually working version of that. So if I fail to implement that, I will still show you the demo, hopefully. Yeah, but so there is a cool Python script that is called the CCM. It basically lets you create as many Cassandra instances in one cluster as you want. It's really simple to use and really works great. Basically, something we discovered not that long ago. So I'm going to see what is running. So according to this, my Cassandra cluster is running, but I'm still going to stop it. There is a flaw in the trigger. Well, basically, for that trigger that I showed you before to work, you need to have it deployed with every Cassandra instance on every node in a conf triggers directory. The best way to do it is by creating a so-called Uber jar or assembly jar, and it will be detected and loaded, and you can then define it in your schema. But I already did all that, so I'm not going to show you how to do that, although there is no documentation for that, so you have to kind of guess. So I stopped the cluster. I'm going to see if my rabbit instance is working. It is, but I'm still going to kill it, or I won't, and see if it's there. Of course it's there. It's always there. And it's gone. Yeah, so let's launch it again. Unfortunately, the rabbit has to be running when you launch the Cassandra cluster, which is really stupid, but that's the way I implemented it. Sorry for that, because when Cassandra loads your class, that class basically, it will try to load the trigger. It will fail because the rabbit is not there, and it will not say anything. So. And now for the cluster. It's going to probably print out some errors, which I don't even understand, but the cluster will be up, hopefully. Yeah, don't look at that. And we can try to connect to the first node using a SQL SH, if I'm not mistaken, and we're here, and we can switch to to-dos. That we will need for later. So,
could you go into presentation mode?
Yeah, I know about this feature. I've seen it once. Yeah. Cool, although it is huge, but anyway. But this is not the class we are looking for, and we want to implement the repository starting from the bottom. So we will be using, as I said before, Phantom. And so yeah, this class will be the class that defines our schema on the Cassandra side. So what we say here is that this extends a Cassandra table. So now the boilerplate starts because you have to write something like that. This says that our Cassandra table is defined by this class, and that our model object is the to-do. So I have already that implemented, as you see on the slide. So we will not be talking about that anymore. And so the fields of the table are actually objects inside of that class, which is kind of weird, but it works. So the first one is user ID, because we always need the user ID, and this is a long column, because why not? And again, this is for this class and this object. I will give you that, and this basically extends a partition key. So what is a partition key? Right, it actually makes sense. Partition key. Partition key of a long type. Yeah, cool. So the way the Cassandra works is basically this so-called column family. You can think about it as a hash map of sorted hash maps. No, there is no such thing. But anyway, a hash map of tree maps. That's the thing I was thinking about, and that's basically it. You have two keys that you can fetch a object by, and that's the partition key. This has no order because you never know on which node your key is. Well, your object is, because those keys are obviously hashed and distributed according to the hash function you define on your cluster. And yeah, so we're going to be using that for the partitioning. But the nice feature of Cassandra is that it has another key. So the first one was called in the 3 times the row key, and this one is called the column name. But obviously you don't need to know that right now. And we will use an ID of the to-do itself, and that's going to be a time-based UUID. Why time-based? Because you want to prevent an order in which actually a reversed order. So the to-dos that you created last will be first on your list. And this already extends something again. So this is going to be mixing in a primary key. That's what it's called now. Yeah, that's UID with cluster ordering, just to inform Phantom that I know that underneath there is a cluster order defined in the schema. So if that's true, then Phantom will allow me to order by that column name. The obvious consequence of that is the whole row under one row key lies on one node. So you have to remember that while designing your model. If you have a lot of, for example, if you have only one user that has a very large number of to-dos, then you probably should redefine your model and don't use that. So a part of that, we also have a, what do we have? We have a done indicator, and that's a Boolean column. Boolean column of to-dos for to-dos, for to-do. And this, it doesn't do anything, it's just a value. And another, and it's the name of the to-do or text or whatever you want to call it. And basically, it's not whatever because those have to match the names of the columns in your schema in Cassandra. To-do. And last but not least, you have to create an object that extends your class. And that's all the boilerplate. No, I forgot about one thing. You have to define how your Cassandra schema actually maps to the model object, to the case classes. So we want to create a to-do that has an optional ID. So we will be not using, in this case, the user ID. We'll only be using the ID of the to-do. And this is an ID of row. And I think name comes first. So this, and done is last. Cool. Although it doesn't really mean anything that idea is not saying anything, because idea most of the times just doesn't work. But, so you can now select. Well, actually, before I start implementing those, I will actually launch that. Not here. I will launch that and see what happens. Because Play has this nice feature of detecting changes if it's in the run mode, and recompiles. If it finds any changes, it will recompile the whole project and restart it, which is nice. So let's see now. It's going to be user number 1. And we should get a very nice error here, hopefully. Well, it's doing something. Yeah, not implemented. So that's because those questions mark here. I already have a controller that actually displays that page that I'm trying to hit. And the only part missing is this implementation of the repository. So we're going to select where user ID equals user ID. And we're going to order that by ID. And that order is going to be descending. And we're going to limit, just in case. And we're going to fetch that. And that's it. Pretty good, isn't it? And that should work now. Yeah. So obviously I cannot do anything else because I haven't implemented anything else. If I've opened the console, you will see errors while trying to add a to-do. So that's because a controller method is missing, but I'm going to first finish the repository. So to select a one to-do, we just do the same thing, basically. First the user ID, user ID, then end. And now we are looking for a given to do. So this has to be an ID. And yeah, we only need one. Or none, obviously, but that's something the Phantoms does for us. We don't need the delete method. And yeah, so the add or update is a bit more complicated, but not that much because it's an add or update. So you have to be sure that the to-do has its ID set. So we're gonna do something like that: get or else. And there is a convenient method new ID that I implemented earlier, but that's not really important. And now we want to insert that into our table. And that's going to be user ID is given by the method. The ID is given by the to-do, or we just actually created one. And all other fields are, the first one is done, are from to-do. And the last one is name. Yeah, and after that we need to execute that with the future. There is a funny thing about this, Phantom library. Actually, you can use both Scala futures or Twitter futures. So you have to be careful which method to call. But at some point, it's really easy to remember. And after that, we want to map our future to the to-do, but we need to be sure that it has the proper ID set. Yeah, but our application is still not going to work because we need to implement the controller. So this is play, basically. It's going to be a little boring for those who know how to use play, but please don't leave. So we're going to find all by the given user ID. There's obviously a routing file for that as well, but I'm not going to get into that. And we're going to set the default limit for 10. And we're going to map the result, and those should be our to-dos, to an OK response with a passed JSON. So using those rights I have implemented on the slides, this will automatically create a JS value, which is something play knows what to do with. So now the add method, and that's going to be pretty simple because our to-do repository just will call this method with a given to-do. Yeah, well, the to-do we have to get from the request, obviously, but it's already a JSON request, so we have that going for us. And we will return this to-do because maybe the ID has been set as the result. Again, JSONizing first. And that's that. So the done logic is a bit more complicated, although not that much. So we first need to fetch the UID you are looking for, the to-do we are looking for by the UID. Then we're going to flat map it. In case it's a none, we're going to return a future successful that says, sorry, it's just not there. And otherwise, if there is a to-do, we're going to, first of all, well, basically update that to-do for the given user ID with the done parameter set to true. And again, this returns the to-do, and we're going to JSONize it. That's it. So the delete one is not really important, and socket is for later. And yeah, so let's refresh the page. Hopefully I haven't done any mistakes. Oh, actually, it seems to be okay. So are we good? Yeah, we are good. Obviously, there is one piece missing. This is not a real-time application, right? Because we added the to-do and we never got the notification that it was added. I actually refreshed the page to see that to do on the list. So we don't want that. And so yeah, we need to implement a logic that will basically get those messages, hoping that the trigger is working correctly, get those messages from Rabbit, and push them back to the WebSocket. So for that, we obviously need an actor. So let's call it the stream consumer. And it's a normal actor. And it has to have the receive method. But let's also define a protocol in which you talk to that actor, because not only Rabbit will be talking to it. So first of all, we have a case class that is a register request for a given user ID, register me, an actor, to listen to the changes of to-dos of that user. And obviously, I need to unregister. Why am I doing this? Basically, whenever a new WebSocket connection is requested in play, it creates an actor that will be using that, basically will be listening to that connection. So there is an actor that lives only through the lifespan of the WebSocket session, and we basically only can talk to it. So, well, in our case, let's not get into that, but so I need to register that actor in another actor in this scenario, which will listen to the Rabbit and forward those messages to the WebSocket. So, right, as an actor goes, we know it can have a mutable state. So let's have that. Actually, I will call this refs. And it's going to be a mutable hash map of longs and sets, also mutable sets of actor references, and it's going to be with the mutable multimap, or just multimap. I don't remember that. Multimap. That's not that, so it has to be mutable. Aha. First of all, I forgot about the new. Probably there is an apply method somewhere, but let's not get into that again. And this extends a multimap. A mutable multimap. Come on, guys, help me here. What am I missing?
Don't use mutable.
Actually, good point. But this is inside of an actor. And how do you define an actor?
System or in a parent actor.
No. How do you define what is actor? As a definition, it's something that has its messages and its state. And only those messages can mutate that state, but they can. So basically, an actor can have a mutable state.
Yeah, well, you could have a state in a receive function, right? As an argument.
Yeah, but so you are talking, for example, about the final state machine, which I could use here.
Yeah.
Yeah, but underneath is still a mutable state. So, and we are not getting to FSM right now. So, yeah. So, what's the problem here? Anyone knows?
Yeah, so I'm not sure what class are you looking for, but I think we should
so you can mix in
instead of extends.
Sorry? Yeah, it should be with, because I'm creating a new instance. You are correct, obviously. And multimap. Thank you, of an actor ref. So this is just a mixin that lets you, in a more easier way, add things. Well, we all know what a multimap is, right? It has a list, but you don't have to know about that because it will be created if it's absent by that trait we just mixed in. So, case we receive a register message of a user ID. We obviously need to import the protocol. Let's do that. user ID and the ref, we're going to say our refs are the binding for that user ID and this ref. Yep. And if it's on register, same case, we're going to say refs remove the binding of the same ref. Yeah, and a part of that we need to also react to the things that come from the stream. And from the stream we will be receiving something that is called a to-do event. So it's just a wrapper around to-do, which also contains the user ID. And this solely comes from the trigger. So this one has a user ID and can have, but doesn't have to have, a to-do. And yeah, so for a given user ID, get or else user ID. And this is gonna be set empty, that should work. And for each, we're gonna just send that to do. And that's it. So let's define the stream in terms of Akka stream. So we already have the actor, so let's call it the consumer. And actor system, actor of properties of a stream consumer. Cool. And now the Akka stream part. So first of all, this will be our sink. So the messages will be coming from Rabbit, the source here. And through the serializer, which I haven't written yet, although, to be honest, I could just say that this should be a to-do and implement a marshaller that comes from the OP Rabbit library. But I don't want to do that because I want to use my JSON rights. And also, I want to have a good example of how can you do a reusable, acknowledgeable stream flow. So, but first of all, let's create that sink. It's going to be a sink based on an actor reference. That's our actor reference. And there is no incomplete message because this stream will never complete, basically. So we will call our acknowledged flow that will deserialize our message. We will call it the deserializer, because why not? And it's going to be an asked flow that accepts the string, then maps it so that the JSON parser can pass it. After that, maps it so we can have a object, a case class from that. Obviously, I could use only one map here, but that's not the point. It's just that you can see, you can basically chain as many transformations you want to. So, but the whole flow will be as follows. So, from source via the deserializer. So, if the deserialization works, we want to acknowledge that stream and to sync. And that's it. That's how you create a stream using a reusable flow. We can use that flow, for example, for something else if there is a place that we have other stream of to-do events. In theory, you can have something like that, right? And we execute that flow. So the only part missing right now is to combine that, that stream with the controller itself. Yeah, so let's do that. So as I said before, this here creates a actor, and we define the actor, and we just say that this actor is of properties of something. So let's create that actor. We're going to call it a WebSocket actor. I think this is more correct. No. And this is a normal actor again. And it really doesn't do anything. A part of that, it has some fields. The first field is the user ID, because that comes from the URL of the WebSocket. So we have to have that in the actor. It's going to be fixed once the actor actually starts after we create a WebSocket connection. A part of that, we need to have the WebSocket itself, which is basically another actor. Well, it is, but this is how we see it from this perspective, and we also have to have something to register at another actor. And yeah, so this will only, if all goes well, only get a to-do of the type to-do. And all that it has to do is send that to-do, well, basically JSONize it, because to the WebSocket, because we here define that this speaks in JSON. But it has to, at some point, register in that stream. So let's see what we have here. We have the pre-start method, in which we can say register at, register me. Register, yeah, that's the one. For that given user ID, and just me. And obviously, when the WebSocket closes, we need to unregister. So register at, unregister, user ID, again me. And last but not least, we create the props class of this actor we just created, and the parameters are user ID, the WS, the WebSocket actor that comes from play, and the actor that we created earlier, and that comes from the to-do stream consumer and consumer. Yeah. So this should now work as expected. Hopefully it will. Okay, compiles, that's good.
So it works.
Yes, we are good. I haven't done a refresh. I hope you believe me. I can do it one hand, so I can do something like that because we also implemented the endpoint when you can say that this is already done. And so, is this real time? Yes, this is real time. Everything that changes in the Cassandra is presented to the user in real time. This is basically responsive. That's what you should call it. Does it scale? That's a good question. So we already have 4 nodes of Cassandra cluster, and I can prove that by saying CCM status. There obviously could be more. So the database scales. Each node, when the table changes, knows how to notify Rabbit about that. Well, actually, we only have 1 Rabbit instance, but I didn't want to create a cluster on my local machine. I don't even know if that, well, basically that's obviously is possible, but so is the web application, does the web application, well, does it scale? So let's see. So we're gonna just launch another instance. No, that's not it. Oh, it's reactive, not active. And we're gonna say, okay, I want this one to run on a different HTTP port, and that's port gonna be that, and we're gonna run it. Yep. And we can say, no, that was actually running on a 9001. No, it wasn't. Cool. Yeah. User number 1. We have a second instance. So let's do something with that. We're gonna do, yeah. So, can you hear me? Yes, I can. And this is a completely different play instance. And it reacts to the same stream, basically because those queues are exclusive. This is not perfect, obviously. Well, it has this good size and bad size. Basically, there is a branch in this project, I will show you the link at the end, but it's basically on my GitHub, which does pretty much the same thing, but using Akka sharding. So there's only 1 queue from Rabbit, and all the play instances listen to that queue, but each stream, each WebSocket actor is distributed. No, the stream consumer, obviously, is distributed across a cluster of Akka actors. So with a given hashing function, there will be only one actor that actually sells to-dos for a given user in the whole cluster. So you can look at that. I will not show you that here because we are kind of running out of time. What else is nice? I had a SQL session open here somewhere. And I have also a prepared somewhere. This exactly. Yeah, but it's not going to be easy to show. But what can you do a part of that? Oh, maybe there should be another option here. So, oh, exactly. Yeah, you can actually. So you can see this, right? So this is important. You can say, hello from Cassandra, and this will arrive here. So you have, if you have a completely different client, for example, for your application that bypasses your application or your web framework, you will still notify all the users on your application that they are using at the moment, also those that are using this application through your web application. So yeah, it's cool. I mean, it's nice to know that you can actually do stuff like that. And yeah, no, I don't want to do that. So basically, that's it. It's kind of nice that it worked the first time. I do have some more slides, though. Sorry for that. Yeah. So that was the demo. I hope you liked it. There is this, again, the most important part, in my opinion, of the reactive manifest is that your application doesn't only have to scale. It has to scale on all levels, like a fractal or something, right? If you look at the database alone, it also has to scale. And that's something we actually managed to achieve here very easily and very quickly using the Play framework, Cassandra, RabbitMQ, and a bit of Akka. That stream part is not really necessary, but again, it's fun. So now I need to tell you something about the company I work for, because I was obligated to do that, and actually I do want to do that. So we are a global market research company. The HQ is in London, so it's a British company basically, but we are present all over the world, on all continents. We gather people opinions, basically, using the internet. The company was founded 15 years ago, and it was the first market research company that was solely using the internet as the source for the data. And those are the technologies we are using at YouGov, all of them, most of them heavily. What we do in Warsaw, in the YouGov Poland office, is only a tech office. Unfortunately, we don't have a market research panel yet in Poland, but it's coming. So the thing we do, we gather the data using pretty much the cool stuff I showed you today, but we also analyze the data using some other cool stuff like Spark and Elasticsearch, everything you want to, you really want to use at the moment. Those are all very cool, very new, and very nice technologies. We utilize most of them. We have a huge, for example, for Spark, we are using AWS Spot instances. We have a snapshot of data that is 100 gigabytes of size, so it's not really that huge, but you do have a repetitive algorithm that relies heavily on the fact that Spark can cache things in memory. So this is running quickly, and it generates data based on what the user has told us. And the user can speak with us, can talk to us by creating an account on our website. And one of the options is so-called mini surveys, when you just have to answer a few questions about the current events. But you also have something that is, well, I don't really have a slide of that, but you can log in, you can look around. It's basically kind of social network in which it basically focuses on what people think about stuff, any stuff. You can actually add your own stuff just to express your opinion about it. It's movies, music artists, it's politicians, it's political parties, anything you want to state your opinion about. After that, we gather all the data and we give it back to you analyzed. For example, this is so-called profile slide. It says, what is the most interesting fans think about the fans of Foo Fighters? And we have 80,000 nodes that we analyze at the moment. Those are all various things. For example, music groups, but also, as I said, movies, for example. We don't have the Scala programming language, although that would be interesting to see, for example, what is the favorite music artist of Scala developers. Wouldn't that be nice? But you can look up any other stuff you want. Again, it's on the web page. The web page is just YouGov. Well, actually, it's not YouGov.com because that's the US instance. Well, we actually don't have a global kind of approach to all of our panels because each panel is different. So for the US site, it's today at todayyouGov.com. For the UK, it's CO UK. And yeah, pay a visit and see what you can find interesting on that website. You can find me on GitHub. Those are two repositories that I presented today, reactive to-dos. I really encourage you to look at the sharding branch because the Akka sharding is also kind of new stuff that is very interesting and very nice. And the trigger, which I don't really encourage you to look at, but if you want to, you can. So yeah, if you want, you can reach me on the mikołajwielocha@yougov.com. If you want to speak with us for any purpose, you can find us on poland@yougov.com. So yeah, any questions? That's the last slide, yeah. No questions. I don't know if that's good or bad. Okay, so thank you very much. Thanks.